In the vast expanse of the universe, where mysteries continue to multiply and the very fabric of space-time stretches out seemingly without limit, a profound enigma has emerged. This puzzle centers on how we can accurately understand the universe's expansion, as we reach an intersection where new data is challenging long-established theories, suggesting hidden forces that could potentially reshape the core foundations of cosmology. Join us on a journey through the latest discoveries and significant leaps in understanding as we explore one of the most captivating and contentious questions in modern science. How fast is the universe really expanding? For over a decade, two separate methods of measuring this expansion have been at odds, leading to a growing debate in the scientific community. The universe's current rate of expansion, known as the Hubble constant, appears to be about 9% faster than predictions made using data from the early universe. Scientists had hoped that the James Webb Space Telescope, the most advanced telescope ever created, would help clarify this issue. However, despite its remarkable precision, Webb's data has only deepened the mystery, presenting observations that challenge the standard cosmological model. This growing divergence in measurements has sparked a conversation about whether we need to rethink or even replace the 40-year-old cosmological model that has guided our understanding of the universe. New physics, possibly involving unknown forces or properties, might be needed to explain these discrepancies. There is a strong sense that we may be overlooking something fundamental about the universe. Let us delve deeper into the new and groundbreaking images from the James Webb Space Telescope, which have recently confirmed that our understanding of the universe may be fundamentally flawed. The universe began with a massive explosion, the Big Bang. This event set into motion the creation of energy, mass, and space, all appearing in a fleeting moment. From there, the universe evolved into a hot, dense plasma of matter and antimatter, which, under normal circumstances, would have annihilated itself. However, a mysterious imbalance allowed more matter to form than antimatter, preventing the universe from collapsing under its own weight. As the universe expanded, gravity caused pockets of plasma to compress and heat up, creating sound waves traveling at about half the speed of light. These sound waves, known as baryon acoustic oscillations, moved across the plasma, shaping the early universe. Meanwhile, the high energy density of the early universe and the gravitational pull of its objects caused space-time itself to stretch, pulling certain regions of the universe apart as the universe inflated like a balloon. The widely accepted story of cosmic evolution suggests that as the universe cooled, matter and light began to combine, forming the first stars and galaxies, which became connected by a vast cosmic web. As these objects expanded, the universe's energy density decreased, slowing the rate of expansion. However, about 5 billion years ago, the expansion rate began accelerating once more, driven by a mysterious and invisible force: dark energy. The simplest and most widely accepted explanation for dark energy is that it represents a cosmological constant, a form of energy that remains the same throughout space and time, woven into the very fabric of spacetime itself. Einstein referred to this as lambda in his general theory of relativity. As the universe has expanded, its matter density has decreased, while the density of dark energy has remained constant, making dark energy the dominant force driving cosmic expansion. Together, the energy densities of regular matter, dark energy, and light energy determine the speed at which the universe expands. These components also form the backbone of the lambda cold dark matter, lambda CDM model, which describes the evolution of the universe and predicts its ultimate fate, an end known as the Big Freeze. While lambda CDM has made remarkably accurate predictions, it is increasingly under scrutiny. Despite extensive research, scientists still don't fully understand what dark matter and dark energy are. As Ofer Lahov, a professor of cosmology at University College London, puts it, the current model posits that the universe consists of 5% regular matter, 25% cold dark matter, and 70% dark energy. However, the problem lies in the fact that we have little understanding of the latter two components, which constitute the majority of the universe's mass-energy content. Moreover, a growing challenge to the lambda CDM model has emerged, particularly in the form of a discrepancy known as the Hubble tension. According to measurements of the early universe, the rate of expansion appears to be much faster than predicted by lambda CDM. This disagreement, verified by multiple independent observations, suggests that our current understanding may be incomplete. One of the key methods used to measure the expansion of the universe is the cosmic microwave background, CMB, which is the residual heat from the Big Bang. This faint signal, detectable across the entire sky, provides crucial information about the early universe. The European Space Agency's Planck satellite, which studied the CMB, has helped cosmologists measure the Hubble constant with remarkable precision, yielding a value of approximately 67 km per second per megaparsec, MPC. This means that for every 3.26 million light-years, 1 megaparsec, away from us, a galaxy is receding at a speed of 67 km per second. However, the Hubble tension becomes evident when we look at more recent measurements of the expansion rate using other methods, such as observations of supernovae and the distances to galaxies. These measurements suggest a Hubble constant closer to 73 km per second per MPC, a value that is roughly 9% faster than the Planck measurements. This discrepancy has led some scientists to speculate that there may be unknown factors at play, potentially indicating new physics or the need for a revised cosmological model. As astrophysicist Adam Rees, a Nobel laureate and leader of the team behind the James Webb Space Telescope's latest observations, notes, "The only explanation I can see right now for why they differ is that our model might be missing something." This indicates that more than just radar measurements are needed to understand the true rate of expansion. To summarize, the universe's expansion rate remains a topic of intense debate and investigation. New observations, especially from the James Webb Space Telescope, are challenging our current models and raising questions about the fundamental forces that govern the cosmos. As we continue to push the boundaries of our knowledge, one thing is clear: the universe holds many secrets yet to be uncovered, and understanding how fast it is truly expanding may be key to unlocking the mysteries of space itself. Gravitational lensing plays a critical role in shaping our understanding of the universe's fundamental boundaries. This phenomenon occurs when the gravitational field of a massive object distorts light from a background source, acting as a natural telescope. By studying the degree of this light bending, cosmologists can infer the mass distribution of galaxies and galaxy clusters, thus refining our knowledge of the universe's large-scale structure. Ongoing surveys like the Dark Energy Survey (DES) and the Large Synoptic Survey Telescope (LSST) aim to map the distribution of galaxies and dark matter across vast regions of the sky. These surveys use advanced imaging techniques and data analysis methods to track the cosmic web, an interconnected network of galaxies and clusters spanning billions of light-years. By focusing on the distribution and clustering patterns of galaxies, astronomers can further challenge cosmological models and refine estimates of parameters such as dark energy density and the Hubble constant. The quest for precision in cosmology extends beyond observational astronomy into theoretical physics, where efforts are underway to develop new models that can explain the observed inconsistencies in our understanding of the universe. Modified gravity theories like modified Newtonian dynamics, MOND, and emerging gravity models offer alternative explanations for cosmic acceleration without invoking dark energy. These theories challenge the standard lambda cold dark matter, lambda CDM model, but definitive observational support is still lacking. Concurrently, particle physics experiments aim to directly detect dark matter particles, proposed constituents that interact weakly with ordinary matter and electromagnetic radiation. Underground detectors like the Large Underground Xenon (LUX) experiment and the Cryogenic Dark Matter Search (CDMS) are designed to capture rare interactions between dark matter particles and atomic nuclei. Success in detecting dark matter would revolutionize both particle physics and cosmology, providing crucial insights into the composition and evolution of the universe. The intersection of observational cosmology, theoretical physics, and experimental particle physics highlights the interdisciplinary nature of cosmology. Collaborative efforts across various scientific fields are essential for advancing our understanding of celestial phenomena and addressing fundamental questions about the universe's origin, evolution, and ultimate fate. Cosmological simulations also play a crucial role in testing theoretical models and interpreting observational data. High-performance supercomputers simulate the formation and development of galaxies, clusters, and large-scale structures in the universe, using initial conditions derived from observations. These simulations allow scientists to explore a range of cosmological scenarios and compare them with actual data, refining our understanding of cosmic evolution and structure formation. Theoretical advances in cosmology also include efforts to reconcile quantum mechanics with general relativity, two cornerstones of modern physics that describe particle behavior on microscopic scales and the dynamics of spacetime on cosmic scales, respectively. The pursuit of a quantum theory of gravity, such as string theory or loop quantum gravity, aims to unify these fundamental theories and provide a comprehensive framework for understanding the universe from its earliest moments to its current state. At the forefront of observational cosmology are space missions and ground-based telescopes equipped with cutting-edge instruments. Despite nearing the end of its operational lifespan, the Hubble Space Telescope continues to make groundbreaking discoveries about distant galaxies, star populations, and the cosmic web. Its successor, the James Webb Space Telescope, JWST, promises to transform our understanding of the early universe, star formation, and the atmospheres of exoplanets. Scheduled for launch in the 2020s, JWST features a larger mirror and enhanced infrared capabilities compared to Hubble, allowing it to peer deeper into space and observe fainter, more distant objects. By studying the infrared signatures of galaxies and protostellar clouds, JWST will provide new insights into the processes that shaped the universe billions of years ago. In addition to space-based observatories, ground-based facilities like the Atacama Large Millimeter/Submillimeter Array, ALMA, and the Square Kilometer Array, SKA, are poised to expand our understanding of the universe's cold and radio-emitting regions. Located in the Chilean Andes, ALMA observes the universe at millimeter and submillimeter wavelengths, revealing the atomic structure of interstellar gas clouds and the formation of planetary systems. Meanwhile, the SKA, an international radio telescope project, will consist of thousands of dishes and radio antennas spread across multiple continents. By mapping the distribution of neutral hydrogen gas and studying cosmic magnetic fields, SKA will explore the cosmic dawn, the epoch when the first stars and galaxies formed, and investigate the role of magnetic fields in shaping the development of large-scale cosmic structures. Cosmology remains a dynamic and exciting field, driven by technological advances, theoretical developments, and collaborative efforts across disciplines. From investigating the nature of dark matter and dark energy to unraveling the mysteries of cosmic acceleration and structure formation, researchers are poised to make transformative discoveries about the inner workings of the universe. As observational capabilities continue to improve and theoretical models evolve, cosmology will undoubtedly remain a vibrant and transformative area of scientific inquiry, offering profound insights into the origins and nature of the universe on the largest scales imaginable. The universe is expanding at an accelerated rate, with galaxies moving away from us faster than the speed of light. One technique to track this expansion uses pulsating stars called Cepheid variables, dying stars whose outer layers of helium expand and contract as they absorb and emit radiation, causing them to blink periodically like distant beacons. In 1912, astronomer Henrietta Swan Leavitt discovered a key relationship. The brighter a Cepheid star, the slower it flickers, allowing astronomers to measure a star's intrinsic brightness and, consequently, its distance. This was a breakthrough discovery that made Cepheids essential standard candles for measuring the vastness of the universe. By combining observations of Cepheid variables, astronomers can estimate immense distances, progressively taking them further back in time. This method remains one of the most reliable tools used today for measuring cosmic distances and constructing a cosmic distance ladder. Astronomers first build the ladder by measuring nearby stars and calculating their distances based on their light. Wendy Friedman, an astrophysicist at the University of Chicago, explained that subsequent steps rely on only Cepheid variables. They then measure the distances of stars and supernovae, using the redshift of their light, how light stretches to longer wavelengths as the universe expands. This technique enabled an accurate measurement of the Hubble constant in 2019. By focusing on the Hubble Space Telescope's observations of a nearby galaxy, the Large Magellanic Cloud, researchers found a surprisingly high expansion rate, 74 kilometers per second per megaparsec, compared to previous estimates. However, due to the chaotic regions of space being studied, there were some blending of distant Cepheids with nearby stars, raising concerns about possible errors in this result. When the James Webb Space Telescope, JWST, launched in December 2021, it was poised to either confirm this discrepancy or resolve it. JWST's mirror is nearly 3 times larger than Hubble's, and it can detect objects almost 100 times fainter, particularly in the infrared spectrum, allowing it to observe a wider range of wavelengths. By comparing Cepheid variables observed by JWST in the galaxy NGC 4258 with those of bright Type 1 supernovae, another kind of standard candle, astronomers produced a similar result to previous measurements: 73 km per second per megaparsec. Other methods, such as using the rapid brightening of a red supergiant or gravitationally distorted light from massive galaxies, return values of 69.6 km per second, 66.6 km per second per megaparsec, respectively. These consistent findings raised further confusion among cosmologists. Rong-Jen Kai, an astrophysicist at the University of California, Merced, who worked on interpreting the Hubble constant, pointed out that the cosmic microwave background, CMB, a remnant of the Big Bang, has been measured with 1% accuracy, and the distance to Cepheid variables is well understood. The CMB provides crucial insights into the universe's early conditions and its ongoing expansion. This radiation, first detected in 1965 by Penzias and Wilson, appears as a uniform glow, with slight temperature fluctuations. By studying these variations with precise instruments, such as the Planck satellite, scientists have gained valuable information about the universe's age, structure, and evolution. The analysis of the CMB has led to a Hubble constant estimate around 67 km per second per megaparsec. However, discrepancies arise when comparing these results with other observational techniques, such as those using Type Ia supernovae or directly measuring the distances to nearby galaxies. Type Ia supernovae, which also serve as standard candles due to their consistent brightness, allow astronomers to check vast distances and indirectly measure the expansion rate of the universe. Despite the small differences, recent observations, both from the Hubble and James Webb Space Telescopes, have highlighted slight variations in the Hubble constant, which continue to puzzle cosmologists.